Welcome everyone. Today we're going to learn squeeze theorem, sandwich theorem. So, let's assume that we have three functions, hx, fx, and gx. If hx is less or equal to gx, and the same way gx is less or equal to fx, we can now, when this condition, when this equation is correct, when this is satisfied, we will check the limit of hx and fx as x approaches to a, and if these limits are equal, the limit of gx as x approaches to a is also going to be the L. The L is, we're working in real numbers, the real number, so let's say L is in the set of R. So, this is true for any limit. It doesn't matter if it's approaching to a from the left side, right side, if it's approaching to infinity, negative infinity, does not matter. So we have a graph to visualize this better. So from the graph, we can clearly see that limit of fx as x approaches to a is L. And the same way, we can clearly see that limit of hx as x approaches to a is also L. And now the squeezed function we have is gx is in the between of them without evaluating the limit of it there. Let's write it with the pink color as well. Limit of gx as x approaches to a is also going to be L because it's the function between these two functions. And we can clearly see the graph of it that this is correct. Now we are able to visualize this. Let's try to see how we're going to use this. So sometimes when we use this method, our limit is going to be 0, and sometimes it's going to be different than 0. So when we have, as for example, this is the first type we will learn, 0 times bounded function, if we see this, the first thing we should think of is going to be squeeze theorem. So first of all, we need to pay attention that we cannot use our limit rules here because cos 1 over 0 does not make any sense, right? So we cannot work with this part. Therefore, we will have to think a way to use a squeeze theorem. We want this function to be squeezed into functions that gives the same limit. How to find that function is, we need to start with our trigonometrical function, which is cos 1 over x, and what we know is this is between 1 and negative 1. And now I have this part. Now if I multiply every side with x squared, I can say that this equation is still correct because x squared is clearly greater than 0. I don't have to change the way of the equation. Now, if I check the limit of the functions I have, times minus 1, and if I check the limit of this function as well, this is clearly 0, and this is clearly 0. Therefore, the squeezed function we have is also going to be 0. So, we have another example. Limit of x to the 4th power times cos 2 over x as x approaches to 0. So I clearly see that 2 over 0 is something that I cannot work with. Therefore, we will say we cannot use our limit rules here as well. Therefore, we start with the function cos 2 over x again. And I know this is between 1 and negative 1. Therefore, I can multiply every side with x to the power, x to the 4th power. And when I do this, I check the limits now from every side. And I'm clearly seeing that, this is equal to 0, this is equal to 0. Therefore, the function I have between these two functions is also going to be 0. Therefore, my limit is 0. What we're doing is really simple. We're trying to squeeze the function we have into other functions that gives the same limit. So, I have another function, limit of root x minus 4 times sin 1 over x minus 4. So this is approaching from the right side because if it was left side, we clearly see that the inside of the root is lesser than 0, which is something we don't work in here. That would be in complex numbers, but that's not something we are working with right now. So what we see is something we cannot work with again because 1 over 0. Therefore, I'm going to start with my sin 1 over x minus 4 again. This is clearly between 1 and negative 1. Now I multiply every side with root x minus 4. and here as well. And now I check the limits to see that if I manage to squeeze it. As we said, it doesn't matter if we approach a value from left, right, infinity. If the squeeze theorem is working, we can use it. We can clearly see that this is 0. This is also 0. Therefore, without using algebra or limit rules, we can say that this is equal to 0 as well. So, this is how basically it works. It's not hard to understand. The thing we should do is just try to see more examples and understand it better. Another example is evaluate limit of fx as x approaches to 1 by using that the equation is given to us. So when I look at it, I'm working with an fx function that I don't know. I don't know what my fx is equal to. I don't know what this function is, but I know it's squeezed between two other functions that I could possibly use, because if the limits of these as x approaches to 1, therefore I will also say that this is equal to. So let's check that out before doing anything. Limit of 5 as x approaches to 1 is 5, obviously. And let's try the same for here. 1 square 1 plus 6, 7 minus 2 is 5. We can clearly see that both sides gave us 5. So therefore, without knowing what the function is, we can say the limit of fx as x approaches to 1 is equal to 5 as well. Now we have another limit. We can clearly see we have something we cannot work with, but there's a plus 2 this time. So maybe we should try to use the sandwich theorem again, but we need to be careful about the 2 here. So what I know is sin 1 over x is between 1 and negative 1. And now I multiply every side by x squared, which gives me this part of the function. And now I add a plus 2 to every side as well to get my function. So, okay, now I check the limits. Limit of the function I have is negative x squared plus 2 here. I put 0 for x, I get 2. I do the same here. Limit x approaches to 0. I have x squared plus 2 again, which is also 2. Therefore, I can say this limit is equal to 2 because of this squeeze theorem, or the sandwich theorem, does not matter. So we have another example. Limit of x cubed times sin 1 over cube root of x. We can see that clearly. So of course we will think that because we have 0 times a bounded function, first thing we need to think is the squeeze theorem. So let's see, sin 1 over cube root of x is between 1 and negative 1. And when I try to multiply it with x cubed, now I need to realize something that is really important here. I cannot do this way, because we used to do it with x squared, x to the 4th power. When we do it with these, the equation will not change its way, because these are clearly greater than 0. But for x cubed, it's not that clear that if it's greater than 0 or not. For negative values, this is lesser than 0, which means our equation will change its way. Therefore, to evaluate this limit, we will have to check if, when I approach it from the left and right, do I get the same value? That's what we're supposed to check. So if these are equal, that will tell us that this limit exists, and we will get the answer. So, okay, let's use different color for one. Okay, let's use the yellow for this one. We will use another one for this. So let's start with the sin function again, 1 over cube root of x. This is clearly between 1 and negative 1. And when I multiply it with x cubed, I know that my x cubed, I'm approaching 0 from the left side. Therefore, this is lesser than 0, a little bit, like it's really lesser, but it's lesser. So this will mean that the equation will change its way this time. we have to change the equation's way because we're multiplying it with reverse sign, with a negative sign. So now we wrote it that like this. Now we can actually say that. We can actually evaluate the limit. We're approaching the 0, therefore this is 0. And from here, this is also 0. This means the function between them is going to give us 0, right? So now let's change the color to evaluate the limit from the right side. What we have is, again, the same function, but this time x cubed is going to be greater than 0 because we're approaching from the right side of the 0. Now this is again between 1 and negative 1, and I multiply every side by x cubed. Therefore, I don't have to change the way now because it's greater than 0. This is going to give me 0, this is going to give me 0, therefore the squeezed function I have, the limit of this is also going to give us 0, and from the left and the right we got the same limit, therefore we will say that this limit is equal to 0. We see that a limit of sin x over x, as now our x is approaching to infinity, but still this we can use, as we said, we don't have a special condition to use our sandwich theorem. We can use it for anything. So what we want to do is we will start with sin x. This is going to be between 1 and negative 1. And now, if we divide every side by x, now we don't know this yet, or maybe we talked about this before. I'm not sure about it, but limit of 1 over x as x approaches to infinity is 0 because we're dividing it with we're dividing it by infinity that is going to be way bigger than big, that it's going to give us 0. Or you can just check the graph of it to see it. It's not going to be a perfect drawing, but still it's 1 over x. The graph of this is going to be like, why I cannot, something like this. So, and if I check it's going to infinity, I'm gonna see that I'm getting 0. Even though, so now, from here I'm getting a 0, and from here also I'm getting a 0. Therefore, the limit of sin x over x as x approaches to infinity is going to give us 0. Now, I will share a question that I want you to solve this time actually. The question is, limit of x times sin x as x approaches 0. I want you to, I know you can solve it without the squeeze theorem, but I want you to use squeeze theorem to evaluate this limit. I will share the solution of this in the comments, but I want you to try to figure this out with squeeze theorem by yourself before it.